And if it passes the guard, it's going to jump over the return. So taking all branches is usually going to give you way more coverage than taking none of the branches, because you'll probably hit all guards in return and nothing will happen. So here's an example of just a little bit of C. If there's less than 2 arguments, you exit, and if not, you print 23C3. So if we take a quick look at this in assembly, I've edited out the instructions that don't really apply to the logic, like stack manipulation and whatnot. So in the first line, you're comparing argc with 1, and it says if it's jump then greater, then you're going to jump past the guard. So if it's 2 and above, it's going to jump past the guard. And if it isn't, it pushes -1, which is all Fs, onto the stack, and then it calls exit. So here's an example of a guard in assembly where the failure of the guard drops through, and taking the branch is going to get you to the rest of the code. So that's one way that people have done stuff, and you're going to find some stuff that way. Another way to choose branches, there was a tool called Prefix, and it randomly took branches. Microsoft bought this tool, I think around maybe 2000, if I'm not mistaken. It was bought by Microsoft and it was shelved. Lots of people still run this tool because you can't get it anymore. They're not releasing it, and basically it just picks random branches, and it goes through. There's some problems with it that you're not going to duplicate your results, right? You're going to run it through, and maybe you'll find something. You run it through the next day, and it's not going to find it, or find something completely different. I think beginning with the DDK for maybe 2003, I'm not sure, Prefast came out. Prefast is basically like a neutered version of Prefix. It doesn't do inner function value tracking. It only works in the function. That's not really that useful. So yeah, I've talked to lots of people that still have their prefix, and they love it, and they're not parting with it for anything. So you can take all branches. If you take all branches, you're going to have multiple machine states. And when you take a branch, by the definition of taking a branch, you've set a constraint on the input. If you take a branch and it's, the comparison is this greater than 5, you have to find that the path is going to be greater than 5 for that value. Something else that you need to make sure is that you don't break these constraints later on. If you've taken a path that says it's greater than 5, damn. I'm taking donations. Anyone else want to bring a beer? Just feel free. So you have to just make sure that you don't break your constraints. If you take a path and you say like EAX is greater than 5, don't invalidate it by taking another branch that's going to betray that constraint, because that'll never happen in real life. So here's a little function. This has it's being passed a character pointer, and there's some comparisons done on it, and there's going to be multiple machine states coming out of this. Sorry for how messy it is, but it's really hard to put code on here and allow people to read it. But basically, the first if is checking if x is not equal to 0, and then it goes into that inner comparison, and if it is 0, then it's going to subtract 1 from the size. Within the inner comparison, it's checking if it's not a new line, and it does something with a size. Otherwise, it also does something different with the size. So what are all the potential states? Well, the first state is that x is less than or equal to -1, or x is greater than or equal to -1, meaning that x is not 0. It's also that x is not equal to a new line, and that would make size equal to 2. That's taking the first block and then taking the else. Taking the first block and taking the first if, and that being true. So the next possibility is that x is equal to a new line, and that would make size equal to 3. That's if it takes the first if and it takes the second, the else within that block. And the last possibility is if it just drops straight through the outside else and it just subtracts 1 from size. So we know that x equals 0 and size equals 0. So real code is going to have way more potential states than this. I mean, this is just a simple function. But this is kind of how you create constraints. And later on, when you call other functions and stuff, there's possibilities that these constraints are going to merge. And this explosion can kind of trim down. And that's really what you're looking for. You're trying to minimize the possibilities. Another thing that you can do with this is if you have multiple states, like I said before, maybe there's certain values that you really want to look for. You want to check for negative numbers. You want to check for certain constants, like in Windows.h if you're doing Windows stuff, or whatever, or other things that have had known problems, like you could try a -1, -4, things like that. So going on to inner function tracking, there's basically 2 types of approaches. There's top-down and there's bottom-up. So top-down, you look for an export. Let's say there's a DLL. You're going to start at all the exported functions. Or let's say it's just a regular program. You're going to go into main. And you're going to start there and you start traversing through all the functions. Just like if you're reading code. You start at the beginning, you go through, you take all the function calls, you analyze all that data, and you basically you weave your way all the way down, back up, and go through the whole tree. Here's some sort of pseudocode. All I did was list the function calls. There's other things probably going on in there. So you need to know what these functions do to be able to figure out what the next function up would calculate or perform. So it's not just function calls, but I just listed the function calls because there's not enough room on there to list real code, or else no one can read it. So here's a little graph. This is going to be like the function call graph. On the left-hand side, you have the name of every function, how many times it goes through, and we're going to step through top-down analysis. So first, we're going to start off in main. And in main, we're going to see we have these 3 different calls. So we go here to foo. That's going to call x, that calls y, that calls z. X calls z again. Main calls x, x calls y calls z, and x calls z again. And then again for bar now. So this takes a really long time. Complexity can really explode. This is only this is a really small function. I mean, this is a really small program, and as you notice, z got hit 5 times. A lot of these functions are being hit multiple times. So it's really time-consuming. We're hitting functions multiple times. Z was hit 5 times. A lot of times, what Matt, he's the one that works on this project with me, kind of defines as that, is kind of like taking a yo-yo and throwing it down the Grand Canyon, and you just wait there for a little bit. It's going to take a long time, and then it comes back up. So every time that you go down these paths, you have to do it again, and it comes back up, and again. So this is very CPU intensive, very time consuming. So the other solution is bottom up. And in this, you try to describe each function in isolation. You're going to taint the return values. And you try to store an expression or some type of constraints for a transformation. So whatever input you have, based on constraints, if this is less than this is what this function is going to do. If it's greater than this is what this function is going to do. And you try to keep that cached. So what you're really trying to do is create like a diff. You have a machine state. A machine state is like your registers. Even your stack is part of your registers, because ESP, EBP points to your stack. I mean, your stack gets pointed to by these registers, and everything is controlled through there. So if you have this machine state and you can define your function as a transformation of this machine state where you have input and output, kind of like a black box, but you have this expression. This is what bottom up is all about. So it works well for deeply nested calls. you're basically tainting all the return values, but it's going to require multiple sweeps. So this is the same code. And the first pass, this is a little bit different. The first pass, what we do is we start in main, and we look at all the function calls in main. And if the function calls if they're calling something else, if they're not solved, none of these are solved. We don't know what foo does exactly. We don't know what x does. We don't know what bar does. So none of them are done. We don't have any information about this, so we have to move on. Then we go to foo. This calls x. We still don't know what x is or what x does, so we move on. Same thing with bar. It calls y. We haven't solved y. Y calls z. We haven't solved z yet. And x calls y and z. So there's this pattern. If we haven't solved it, we keep on moving down the tree. Finally, z returns something. It's the leaf node. It doesn't call anything else. So we have an idea of, based on some kind of input, what the return is going to be, and we create this expression. Z is now solved. So we can cache z. We can cache this expression for z. So that was one path down, and it seems a lot like top down, but the difference is that z is done. Z is evaluated as a diff, and the analysis is cached. You don't have to look at z ever again. Instead of before, where you have to go down like with a yo-yo, and you have to go down the call chain and come back up and analyze everything over and over again. You have a definition for z, and it's cached, and you don't have to do that again and again. So here we start on the second pass. We start the same way. We're in main. Foo, x, and bar are not solved. So we have to move on. Again, foo calls x. We don't know what x is. Bar calls y. We don't know what y is. X calls y and z. We know what z is, so we don't have to analyze z again. We have the answer for that already. And we don't know what y is. Once we move into looking at the y function, since we know what z is and it's cached, we have all that information already. We can pass that up, and now we can create an expression for y. So now we've solved two functions within this program. So at pass 2, we have z and y cached. Every time you do the sweep or this pass, you're going to get more and more functions. So I'm not going to step through it again and again, but so after the third pass, this is what you're going to get. After the fourth pass, you solve all this, and after the fifth pass, this is what you have. And this again also, went through multiple iterations, and it's not the most efficient way to do it. It took 5 passes. So this is called bottom up because you solve all the functions at the bottom, and it kind of bubbles up like it's boiling. All your information starts coming up, and as you keep on analyzing it, it keeps on coming up to the top. So some optimizations is you can, let's say you disassemble the whole program. You look at leaf nodes first, because leaf nodes don't call anything else, so this can be solved. So you solve off the leaf nodes. Then let's say you look for functions with low amount of calls. So you look for functions that call maybe one other function, call a leaf node, right? And have lots of cross-references. So you set those on a higher priority, because if it has lots of cross-references, that's going to reach up to more functions. So ideally, what you're really trying to do is combine both these approaches. Both these are different academic approaches. Some people are like, it's top-down or nothing. Some people are like bottom-up or nothing. What we found is the best is kind of like a hybrid of both. It's going to get you the most code coverage with the fastest time. So non-contiguous functions. I don't really see these as a problem for anything. They were a little confusing at first when they first came out to do reversing, but if you look at them, they're just basic blocks. It's just input and output. It doesn't matter if it's in the same continuous address space. It's doing the same type of thing. So, I mean, the only reason we have functions is because that's how